Welcome back. We are in Chapter 3, Section 10. This is the last section of Chapter 3, and it's called Theorems about Differentiable Functions. We often want to infer a global conclusion, and when I mean global conclusion, I mean something like f is increasing on an interval. So we often want to infer a global conclusion from local information. And when I say local information, I mean something like we know that f prime is positive at each point on an interval. So if we know something about each point on the interval, can we make a global conclusion about the entire interval? The following theorem kind of lets us do that. So the following theorem relates the average rate of change of a function on an interval which is some global information, to the instantaneous rate of change of a function at a point on the interval. That's some local information. So this is a theorem you may or may not have heard the name of. So this is called the mean value theorem, and for us this is theorem 3.7. So theorem 3.7, the mean value theorem. So this states if f is continuous on the interval from a to b, so on the closed interval from a to b, and differentiable on the open interval from a to b, then there exists a number c where c is between a and b such that f prime of c is equal to f of b minus f of a divided by b minus a. In other words, f of b minus f of a is equal to f prime of c times b minus a. We get that by just doing some simple algebra and multiplying both sides by b minus a. And a note, the mean value theorem tells us that C exists, but it doesn't tell us how to find C. That's a problem for a different day. For now, we won't focus on that. And there's another theorem, which is kind of just a special case of the mean value theorem, so it doesn't get its own number, but it's called Rolle's theorem. And Rolle's theorem states, if f satisfies the conditions of the mean value theorem, which I'm going to just say MVT, left to right, on the open interval from a to b, and f of a is equal to f of b, specifically both of those are equal to 0, then the mean value theorem tells us that there is a point C where C is between A and B such that f prime of C is equal to 0. So kind of where this came from, remember if we look up here, we said another way to rewrite our mean value theorem is f of b minus f of a is equal to f prime of c minus b times b minus a. If f of a and f of b both equal each other, and they're equal to 0, then f of b minus f of a is 0. So that means f prime of c, regardless of what, so f prime of c has to be 0 because b and a are not the same number, right? We said a less than x less than b, so that means they can't be the same. And so we know a and b are different, so b minus a is not 0, but the left-hand side of this equation is 0, so f prime of c needs to be 0. So that's a little bit about where that came from. And these are useful theorems kind of behind the scenes for us in calculus. Now, a few notes about some vocab before we move on to the next theorem, or set of theorems. We say that a function f is increasing on an interval if for any two numbers x1 and x2 in the interval such that x1 is less than x2, f of x1 is less than f of x2. So if as x increases, f increases, then f is called increasing. If instead we have f of x1 is less than or equal to f of x2, then we can't say increasing. Instead, we say f is non-decreasing. Because it might be the case that f of x1 and f of x2 are equal, so they're not increasing, but they're also not decreasing. So now that we know kind of what this terminology is, we can move on to our next theorems. First up is theorem 3.8, which is the increasing function theorem. So, suppose f is continuous on the closed interval from a to b and differentiable on the open interval from a to b. If f prime of x is greater than 0 on the open interval from a to b, then f is increasing. On the closed interval from a to b. And if f prime of x is greater than or equal to 0 on the open interval from a to b, then f is non-decreasing on the closed interval from a to b. So that's our increasing function theorem. And really, we already knew this, right? We already knew that if the derivative was positive, then that means our slope is positive and our function is increasing. Now we're just making it formal, making it into a theorem. Another thing we know is if f is constant, on an interval, then f prime of x is 0 on that interval. The following theorem is the converse of that. If you don't know what converse means, don't worry about it too much, but a quick Google search will clear that up. So theorem 3.9, start over there. Theorem 3.9 is the constant function theorem. And this tells us, suppose that f is continuous on the closed interval from a to b and differentiable on the open interval from A to B, then f, whoa, sorry, looked at the wrong line. Okay, so again, we're just starting off with the same little sentence we've been starting off with this whole time. It's just anytime you use a theorem in math, there are certain things that have to be true before we can use it. So here we just need f to be continuous and differentiable. So it's continuous and we can take a derivative of it. That's what this means. Because this whole chapter is about derivatives, so obviously we need to be able to take derivatives. So that's all that's saying, is just say we can take a derivative of it. If f prime of x is equal to 0 on the open interval from A to B, then f is constant on the closed interval from A to B. And this whole thing about how I'm switching from open intervals to closed intervals, it just has to do with things not being differentiable at the end points of an interval, and again, not a huge thing for us to worry about. Mainly what you need to worry about is, if f prime of x is 0, f is constant. So we have one more theorem that we will end with, and then we'll do an example of that one. This chapter is a little dry because it's just theorem, 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 but we're about to move into chapter 4 where we actually get to start using all of these things, so it'll be a little more fun. And if you've taken calculus before, a little bit more like the calculus you've seen again. So, brings us to theorem 3.10. And this is the racetrack principle. So theorem 3.10, the racetrack principle. Suppose that G and H are continuous on A less than or equal to X less than or equal to B, so that closed interval, and differentiable on A less than X less than B, so our open interval, and also that G prime of X is less than or equal to H prime of X on that open interval. Then this tells us two things. If G of A is equal to H of A, then G prime of X is less than or equal to H of X on the open interval. If instead G of B is equal to H of B, then G prime of X is greater than or equal to H of X for A less than or equal to X less than or equal to B, so on that closed interval. And if we think about this, we can reason through this and see why this would make sense. So it has the following interpretation. We can think of G and H as two cars on a racetrack. With car H always going faster than car G. So if they start together, then car H will be ahead during the entire race. This makes sense. So we said that car H is always going faster than car G, so if they both start at the same place at the same time, then car H is going to be ahead the whole time. Now, if they end together, then car G must have been ahead during the entire race. So if car H is faster than car G, the only way that they end together is if car G had a head start and was in the lead for the whole race. Let me just double check. Okay, cool. Wanted to make sure I wrote the theorem correctly. Didn't leave off a prime. So this is the interpretation. It can be helpful if we think of these cars literally on a racetrack. That's where this principle gets its name. We can do an example.